Alright, so in this video, I will resume my part or section on inferences, continuing with the concept of a p-value and then moving on to the linear combinations, which is a little tougher than what I covered before, but should be pretty doable. Alright, so what the p-value essentially does is it measures how unlikely the null hypothesis is to be true in respect to the alternative. And similar to our t-statistic or our critical value, I guess, the critical value, like the critical value, it will depend on the sample size, the significance level, or the percent confidence that we were testing for, like 95, 99, 90, etc. And then the type of hypothesis. So whether we're saying like income has a positive effect on food expenditure or negative, or if it even has an effect at all. And then when I say C here, just remember that C doesn't have to be 0. So we might be wanting to find out like, oh, does income have at least a a value of 5 effect over the food expenditure, not 0. That the null hypothesis can be seen like it still does. So it doesn't have to be the null doesn't have to be seen like, oh, it doesn't have an effect at all. It just has an effect of 10 or 5, as we will see in this lecture. All right, so the rejection rule regarding the p-value is that if it's less than alpha, we reject the null, and if it's greater than alpha, we fail to reject the null. And the good thing about p-values is that we can always, it's very fast and efficient because when we use a software like Python or R, it's very clear. The p-value is shown very clearly. We don't have to make a comparison of the critical value and the t-statistic, so that's what it's useful for. Note that the reason why we still calculated, I went over how we calculate the t-statistic and the critical value, is because we need to know that to calculate the p-value. The p-value, as the t-statistic decreases, the p-value, or as the t-statistic increases, the p-value decreases. So we need to know the t-statistic to know the p-value. All right, and so we did mention confidence intervals in the last video, and we can actually use confidence intervals to in a form of hypothesis testing, actually. So we essentially, intuitively, we would reject the null if, let's say we're testing if the beta 2 had an effect at all over food expenditure, if income had an effect at all. And so when we're creating our confidence interval around beta 2, we would reject the null, right, if our beta 2 coefficient resulted in outside of the interval, because if it's outside of the interval, that means it's different enough so that it actually has an effect on beta 2 or on the food expenditure y. So using our first example here, let's so to create a confidence interval, note that it's given by beta 2 plus or minus the critical value times the standard error of B2. And so if we want to calculate that, we found out that the critical value of, we found out that the critical value of our equation in the last video, we found out it's 2, and then the null is saying if So I didn't make it clear here because I just said C, but we're essentially testing if we're essentially testing if the confidence interval is how confident are we that I'm sorry. We're creating confidence interval around the 10, so not 0, because we're not actually testing if income has an effect of food expenditure in this case, but we're creating the confidence interval around 0. Or we're gonna base our beta to around 10, but our null hypothesis is still saying that food expenditure income does not have an effect on food expenditure. So this is my mistake. I should have made this more specific in my notes, but so this is 10 because our given coefficient is 10, and the critical value we found was 2 and then 2. And like again, because our interval is 6 to 14, if our null hypothesis is saying it doesn't have an effect on food expenditure, or the coefficient should be 0, then we reject the null because the 0 is outside of 6 to 14. But let's say like the null was saying, oh, food income has like a 7 effect on food expenditure, not 10. Then we would have to accept it because the null, the C in this case, in that case will be 7, and because 7 is within the confidence interval that we created from the 95%, it's within the confidence interval of what the null hypothesis stated, and based on our 95%. So that means that essentially saying that our null hypothesis is correct because it's not outside of the confidence interval, so we have to accept it, and we can't reject the null. All right, hopefully that made sense. I didn't do a good job of making sense of that, but try to kind of repeat what I was stating. All right, so for linear combinations, let's say instead of creating a confidence interval for just beta 2, let's say we want to create a confidence interval for the whole equation. So essentially what we're asking is, for an income of 100, do we spend a food expenditure of 1,050 of what we calculated in the past? So the null will be saying based on our whole regression function, where our income is 100, our food expenditure is at 1,050, and then our alternative is kind of trying to challenge that. So it's saying, oh, well, our income will not be 1,050, and it won't be close to it either. And so what we'll do is we'll notate the whole linear combination of beta 1, beta 2, and our like 100 coefficient into this Greek letter lambda. So the lambda is representing the whole combination linear regression function of the y equals 10x plus 50 in this case, and our variance of lambda is given here. Our formula is given here. If you want the proof of this, I'm sure it's somewhere on the internet. You can find it in a textbook, but it does look different because our variance of beta 1 and beta 2 is different. So essentially, it will make sense if our variance of the lambda of the whole given linear function is also different. If you're wondering why the coefficient, the C, is like squared, it's mostly because the C originally is within the variance of the beta 1 and beta 2, but then we have to extract it out because the variance has something to do with like squaring the standard error. Recall that when we're measuring the variance, we have to like do like x minus x mean to the squared. So it's kind of in relation to that. But anyhow, and then we have to also account for the covariance, which from what I've seen, people tend to forget a lot. Confidence interval is the same. Our lambda is given by the different terms, but our formula is still the same. So if we use the same example with the same confidence interval and the same sample size, our income is 100, and our covariance is also given, just because the covariance is a little harder to calculate when it comes to the variance and variance of beta 1 and beta 2. I mean, our standard error were also given, so I guess that also makes sense why our covariance of beta 1 and beta 2 were given, but like the variance of beta 1 and beta 2, even though like they are different to find out, or they might be difficult, but I did give the formulas in the previous lecture. But nevertheless, they're the standard errors given and then the covariance of beta 1 and beta 2 given. So given all that, we want to create a 95% confidence interval for our whole parameter, our whole function of the food expenditure. What our food expenditure will be given all these circumstances and given that our income is 100 and all whatnot. So we have our default equation here. We have 1050 because that's what we got out of if we plug in 100 times 10 plus 50 our function, our critical value is still 2 because none of the determinants of the critical value change. So our n stays the same, our alpha stays the same. We're still using a two-tailed test because we're creating the null isn't saying the alternative isn't saying it's greater or less than 1050. It's just saying it's not 1050. So that's the only thing we have to prove. We don't have to prove that it's less or greater. So when we do plus or minus, we have to, the hardest part is the standard error of the lambda. Now I did give the standard error of the variables here, but we have to input those into the formula I gave here because again, it is slightly different for the whole linear combination equation. And so if we plug that in here, we get the c1 squared. Now the coefficient of our intercept is just 1 because it's an intercept. So we can just say 1 squared. Variance of b1. So actually, before I go into this, the standard error, if we want to calculate it, the standard error for the confidence interval, we want to square our variance to find the standard error, right? So given our variance formula, we can actually just square root that in order to find the standard error right off the bat. So doing the square root, we can plug in this formula right here. So 1 of the coefficient of the intercept, because the coefficient of the intercept is always 1. And then the variance of b1, which is 30. Again, this way this will result in the standard error because we're squaring it, so we don't have to worry about that. And so we can just write the variance formula out right here. Coefficient of the beta 2 was 2, or sorry, it was 10. And then the variance of b2, that was 2. Or excuse me, this is a standard error. Just a second. Okay, yeah, so we're squaring the variance because we're squaring the standard error because we have to find a variance. And then once we find a variance, we have to find the standard error again of the linear combination. So it is a bit confusing, but the standard it's easy to understand if you know that the standard errors within these variables are not the standard errors for the whole linear combination of the regression function. So we have to convert these standard errors into the variance function, or these variance terms, and then convert it back into the standard error because this whole equation right here is based on the variance of lambda. So 10 squared times variance of b2 which is 2, or 2 squared, plus 2, 1, and 10, because C1 and C2 we calculated. And then the covariance of B1 and B2 was given, which is 100. Okay, if we calculate all that, we get an answer of 57 around. And so finally, once we get the 57, we can plug that into the standard error of the lambda here. So 57 times 2 is 114. So 1050 plus or minus 114. That turned out to be 935 to 2,920. Sorry, that should not be correct. I don't know how I'm getting that answer. What's one? Let me just do it quickly. So 1,050 plus 57 times 2. Okay. 1,164. And let me just double check that my first answer is also correct. $936. Okay. Let's just erase that. So this is our 95% confidence interval for our whole regression function. So if we have an income of 100, then generally speaking, we are 95% sure that we will spend a food expenditure of 936 to 1,164. Okay, and then lastly, we can also use the test statistic and the critical value for hypothesis testing of the linear combinations. So using the same example of our income to 1,000, we can utilize the t-statistic formula given right here, plug our specific example in of our lambda equal to 1,050. Actually, so our problem is slightly different because what I wrote in this example is that someone is arguing that our food expenditure, it's not a stretch to say our food expenditure is going to be 1,000 if our income is 100. And so that's what we're actually testing for. I mean, it's essentially the same thing because we can kind of argue here that like, if someone says our food expenditure is 1,000, then we have to accept what they're saying because it's within the confidence interval here. But if we calculate that with using the test statistic and the standard error and the critical value, we found out that this value is around 57. So 50 over 57, that's less than 1. And then our critical value, it turned out to be around 2. And so because the absolute value of 1 is less than, or we got a value less than 1, but because 50 over 57, the absolute value of that is less than 2, we'd say the test statistic is less than the critical value, and in that case, we accept the null. Oops. We accept the null that's saying our income is going to be 1,000, because 1,000, even in this case, where we calculated using confidence intervals, is within the interval given from our formula here. So essentially, there are two ways we can use the test statistic and the critical value, or we can use our confidence intervals. Usually, we would use the latter because we will only use the confidence intervals when we are told to. It is a longer process, but like confidence intervals, we're utilizing the standard error and the critical value and all that. So all in all, it's pretty much the same thing. All right, that is going to be in the next video. I don't know what I'm going to cover, or that's going to be for this video. I don't know what I'm going to cover in the next video, but we are done with inferencing. But this is a very important concept, so it will a lot of the lectures I cover in the future will have follow-ups through this. So definitely relearn this if anything like what I said isn't clear. But yeah.